let's talk about a very important example that's very similar to what we've been talking about. We want to count functions. What is a function? A function is just an abstract thing that assigns to elements in some set, which we call the domain, elements in some other set, which is called the codomain. So let's give some names to it. This abstract thing that we call the function, we'll give a name, say f. Let's say that the domain is D and the codomain, I don't know, call it S. And the question is, how many functions are there from an M element set to an N element set? So in order to count them in a way like we're doing in this class, we want these to be finite sets. Though abstractly, one can talk about functions, and you do this all the time in calculus, where the domain and codomain are infinite sets. In calculus, most of your calculus classes, the domain and codomain were the real numbers. You would have real valued functions of a real variable. Sometimes you talked about functions of two variables where the domain was, say, pairs of real numbers and the codomain might have been real numbers. And of course, some of you might have studied functions of a complex variable where the domain is the set of complex numbers and the codomain was maybe complex numbers. Maybe you were interested in real valued functions of a complex variable. Functions are just the abstract things that take elements in the domain and assign them some value in the codomain. You all probably know the range is the set of all elements of the codomain, which actually are values of the function at some point in the domain, all the outputs of the particular function. So here's a question. If the domain has M elements, and the codomain has N elements, how many functions could I possibly create from that domain to that codomain? Well, the answer is pretty easy, again, using the product rule. Let's take a look. In order to use the product rule, let's take a look at it this way. The domain here, D, consists of the numbers 1, 2, 3, 4, 5, all the way up to M. The codomain, which I'll call S here, consists of the numbers 1, 2, 3, 4, 5, all the way up to N. And what does it mean to be a function? The function f will take each element in the domain and map it to some element in the codomain. When I write an arrow like that, that means f of 1 is 2. And maybe here f of 4 gets mapped here. Equals 3. And to be a function, f has to assign a value to each and every element of the domain. It's not true that every element of the codomain has to be in the range, but every element of the domain has to be assigned a value somewhere. So how does the product rule help us? Well, I ask, how many choices do I have for an element that 1 maps to? Well, the answer is n. 1 for element for 1 in the domain, I will get n choices. It can go to any element in the codomain. 2, I'll have n choices. 3, I'll have n choices. All the way to m, I'll have n choices. The product rule says I'll have n to the mth power, and this n times n times n times n, m times total functions. So for example, if we look at a special case, and here we'll think of that special case where the codomain has 2 elements, just 0 and 1, we're looking at a function from some set D, the domain, to the set 0, 1. We're just assigning to each element a 0 or a 1. Well, how many such functions are there? The answer is 2 to the m, because n would be 2 in that case. I don't think I prepared my slides properly, but let me write it right here. The number of functions from an M element set D to the set 0, 1, a 2-element set, is 2 to the M. And that should look familiar because there's the natural mapping from functions from D to the set 0, 1. I'll put this natural one-to-one correspondence. And the power set of D. This is the set of all subsets. How does that natural correspondence work? Well, if you have a function that maps D to the set 0, 1, look at all the elements that are mapped to 1. Say those will be the ones that you might say are in the subset that you're interested in. All the ones that map to 0 are the ones that are not in the subset. So if you give me a function from D to 0, 1, that will be associated with that particular subset that contains all those elements that map to 1. If you start with a subset of D, you can create a function that assigns each of those to 1 and all the others to 0. There's this natural one-to-one correspondence, and that's why just another way to show here that the number of subsets of a set of size M is 2 to the M, the same as the number of functions from that set of size M to the set 0, 1.